All right, so today we're going to be looking at uh, polyatomic ions. Essentially, they're covalent molecules that typically just have extra electrons on them uh, to make everything happy. But when we add electrons to a molecule, we make the whole thing negative. We worked with them with ionic bonding, simply writing the charges, crisscrossing them, figuring out formulas, figuring out names. Today we're going to go through and actually figure out what did those things look like. So PO4 with a charge of -3, that's a phosphate group or phosphate. That is my favorite polyatomic ion. I don't have a reason why, it just is. Really what we're looking at is we have one phosphorus, four oxygens, and we have three electrons to kind of make everything happy. So starting off, so let's go phosphorus, 5 outer shell electrons, 4 oxygens, really spreading out here. Each of them with 6 outer shell electrons, so they each want 2 bonds starting off with. All right, 3 electrons I could put somewhere. Some molecules, it's easier to figure out where these electrons go to begin with. Some of them, it's easier to start bonding things together, figure out kind of where we're going to be lacking. All right, so for this one, I'm just going to start putting some stuff down. From breaking the octet rule, I know these oxygens probably aren't bonded to each other, probably bonded to the phosphorus. So let's just put kind of a phosphorus right there. Um, let's see, we can go, let's just start by just single bonding things and see where I end up. Let's go with a single bond there. Let's go single bond there. And there. Okay. So now looking at this puzzle, phosphorus still has 2 electrons that oxygen can force it to do something with. I have 1 oxygen that still wants 2 bonds here. So let's just go through, let's have that oxygen do a double bond there. All right, so now at this point, my phosphorus is out of electrons to give, it's out of bonds to form. That phosphorus is pretty much done at this point. These 3 oxygens still have an electron that need a partner though. So one of the things I can do, if I do this, we'll make it like that. If I come through, rather than saying these unpaired electrons, rather than having them form bonds, what if we just took, from the formula, I know there's 3 electrons here I can give somewhere to make this thing happy. So let's say I put an electron here, an electron here, and an electron here. Now these 3 electrons look like they have 8 outer shell electrons. The thing of it is though, and I'm just going to circle the ones I added here quick. When I added those electrons to these oxygens though, I've now changed how many electrons they have compared to the protons. They now have 1 more electron. So each of these oxygens, I should say, is going to form a charge of -1. To do that, I'm just going to kind of write it off to the side there. I'm going to throw a circle on it just to draw attention to it. But now it looks like everything's happy. My phosphorus, pretty much happy. It has no electrons or bonds left to do. That oxygen, 8 electrons around it. This oxygen looks like it has 8. Same with those two. I think I'm ready to draw the final product. All right, this phosphorus, 2 bonds to an oxygen. So double bond to an oxygen, which has 2 pairs of electrons. Coming back to my phosphorus, it has 3 bonds, each going to a different oxygen. And I said that was to a different oxygen. And when I look at these 3 oxygens, they all look identical. They all have 1, 2, 3 pairs of electrons, and they each have a charge of -1. So let's start with the pairs of electrons. All right, and we said that they each had a charge -1. Once again, I throw a circle around the -1 just to really draw attention to that. That's what phosphate looks like. Um, this is a really important molecule for chemical manufacturing, uh, fertilizers, when we're talking about biology, like ATP. Um, these are the phosphates that get broken off of a chain to release energy. Um, that's probably why it's my favorite. All right, so I want to look at one more real quick. We're going to look at essentially the one positive polyatomic ion if I quit showing you everything else on my computer. So NH4 positive 1. The positive one means we've taken an electron from somewhere. And I would say let's figure that part out later on. So I have a nitrogen, and I have 4 hydrogens. Hydrogens, of course, are pretty easy to deal with. They each have 1 unpaired electron, so they each want 1 bond. The nitrogen is in column 5, so it has 5 outer shell electrons, wants 3 bonds. All right. Now when I go through to do this, I would say let's just start bonding stuff together and then figure out where am I removing an electron, because chances are, we'll talk about it. So let's go single bond to single bond, single bond to single bond, and single bond to single bond. All right, so now those 3 hydrogens are fine. Nitrogen's used up all of its electrons. At this point, there's 2 ways we can kind of look at this. So let's even draw this where we have throw an H up there, and I'm going to look at it in another way as well. Let's give it 2 electrons. 2 electrons. All right, so the first way we're going to look at it is this hydrogen needs a bond. So let's go ahead. I'm going to rewrite that actually. I'm going to just move that up a little bit. I'm just going to have that bond coming down. All right, so now let's go like that. All right, so the first way we can look at how are we going to remove an electron here? Well, with it looking like this, we could kind of see how if nitrogen kind of gave up that electron there, we could just combine, have that bond to that electron there. And then my nitrogen is missing an electron, so it has a charge of positive 1. That's one way to do it. That's a fine, perfectly acceptable way to do it. That's, I think, the most obvious way to look at it and see. But if we wanted to look at things in a little bit more complex way, some, way that we actually do see, what if we took away an electron from a hydrogen? So now essentially we just kind of have this proton flying around. Now this hydrogen still wants 2 electrons, and it just so happens nitrogen has these 2 electrons that could share right there. So in this case, like let's say we got rid of a electron off of the hydrogen. Essentially what that nitrogen is doing is it's temporarily essentially giving one of its electrons to the hydrogen, and then they're each sharing it. Like ammonia is kind of interesting this way in that we kind of have two molecules, 2 forms that work. They look really identical. We essentially have a nitrogen with 4 single bonds coming out of it, no pairs of electrons. What differs though is where we find kind of this positive charge. It's either on the nitrogen or it's on the hydrogen. Really what we find out in nature is essentially this positive charge. Same thing with the negative charges on the phosphate is they kind of float around. Like it kind of makes the whole thing kind of positively charged. Same thing with these phosphates here is essentially this extra electron that was here, like it can kind of float around and kind of change where the double bond is. So we're going to see that big time with this ammonium here, since they all kind of look identical. All right, so ending it on a very confusing note, but essentially that's uh, drawing polyatomic ions. There's times when we have to combine breaking the octet rule with it. Really, it's whatever our negative charge is, that's how many electrons we have to find homes for on this molecule. And then if it's a positive ion, we just have to figure out where we take an electron from. Good luck with the practice. This should take up the last couple pages in the packet, I think. But with that, good luck.